Hello everyone and welcome to today's Dr. Data Science. We are today Stephen Hillian and Peter Shaw going to present. And as always, please remember we are doing these Dr. Data Science sessions every third Wednesday at 9 a.m. Pacific or 12 p.m. Eastern time. And next session is on June 17th. And after the session is done, we post session recording on YouTube, and I will post the playlist link in the chat shortly. Over to you, Stephen.
Great, thanks, Dinad. I'm particularly excited about today's session because we have a special guest, extra special guest. We always have a special guest, but as you know, Dr. Data Science is not really one person. It sort of represents the sum total of data science wisdom at TIBCO and the TIBCO data science team. And one of the primary sources of wisdom, I will say, if that doesn't embarrass him too much, is Peter Shaw. Peter Shaw has been on the team really since the beginning of TIBCO's data science efforts, and he's actually retiring this year, so we're going to miss him greatly. But I wanted to make sure that everybody who tunes into Dr. Data Science here and on the YouTube channel can get to meet him. So welcome, Peter. As always, we will split the session into two bits. First of all, a little nugget of perhaps common information about data science that is maybe not as well known as it should be, and then we'll have a featured session. Last week we covered, well, usually for the information game, we do a technical topic, but we actually covered recruiting and what makes a data scientist and how to become a data scientist. And our featured session with Tomasz was on using gains and RSC curves and confusion matrices to find the best model for classification. Today, we're going to do a quick info gain on how to evaluate models using cross-validation. And that'll then lead into our featured session, which is about variable selection and how to select the best variable selection technique. And that's what Peter will be talking about. I want to give Peter as much time as possible to talk on an interesting and important topic. So I'll whip through the info gain pretty quickly. Cross-validation, I think, is in some senses something that most of us already know about. The simplest form of cross-validation is just simply using a holdout sample, a single sample to test the model. So that's a way of testing one or more models to see how accurate they are, having trained them on the complement of that set. And that helps to avoid overfitting. So, you know, it's easy to build a perfect model on a single training and testing set. You just get a model that sort of knows every observation, but then it'll be hopeless if you validate it on a separate set. So the idea with this form of cross-validation is that you can evaluate, say, two or more models by training them on one set and testing them on the complement. And that way you can test different models that say different model types, you know, a logistic regression versus an SVM, or maybe you want to test different kernels for the SVM, or test having different variables in your logistic regression, a topic that Peter will cover in a second. Or maybe you want to test different hyperparameters for your model. This is a simplest way of being able to do that. You vary those and see how they compare in terms of accuracy on the holdout. The problem with this method, though, is that you're only training once on a subset and testing once on a subset. You're not testing on the entire data set, and this can be particularly problematic. So there's a tendency maybe for your model to sort of overfit on that single training sample, and especially that's true if your data set is small, because you're just missing out a chunk in training, and you're missing out a chunk when you're testing. So there's another approach called k-fold cross-validation, which is a little better. It sort of generalizes this approach. I've illustrated it here sort of schematically with k equals 3. If you're doing k-fold validation, you're creating k-folds, and I'm showing it here with 3. And the idea is to partition your data set into k distinct subsets that cover the whole set. So a true partition of your data set. And you go through that k times, in this case 3 times, and you train, or you test on one of the samples and you train the model on the other 2. So basically you train on k-1 and you test on the remaining one, and you do that for each of those k subsets. And this way you end up training and testing on every single observation in the data set. And what you can do then is you test using, say, root mean square error or area under the curve or whatever your favorite test is on each of these K samples, and you create an aggregate measure of accuracy, an aggregate over the entire data set. So it's a sort of preferred method. I think it actually tends to be underused. I find a lot of people sort of just use this, and that's fine, especially if you have larger data sets perhaps, but it's a good practice to get into using this K-fold method. And it's usually pretty easy to do. It's usually built into the routine that you're using in Python or R or in the tool that you're using. A couple of other things to think about, right? You also maybe want to consider, once you've done this, also having a final test set, the very final test to make sure that nothing got screwed up along the way. And there's a lot of questions about how to sample, right? So here we're sort of implying you just take a random sample for each of these K subsets, but that doesn't necessarily always work. There are times, for example, with time series where you want to be a little clever about how you sample, but I think that's a topic for another day. Let's move over to Peter, who's going to be talking about variable selection. And maybe I'll sort of start this off, Peter, by just asking you, why do we do variable selection?
All right. Well, thank you, Stephen, for the great intro. Yeah, well, there's a good reason for all this stuff. Let me actually jump into my presenting mode here.
That's good.
And I thought I'd just start off with to illustrate all these ideas with the data set. So in the broader sense, you basically want to do variable selection to avoid overfitting the model. There's other methods that don't involve selecting specific variables, but let's say for the sake of argument, we've got this data set, and this is a public data set of, just for illustration, of some data on bicycle sharing. So, and I hope this isn't going to automatically advance my slide. Anyway, so what we have here is as a function of time, it was back in a number of years ago, so x-axis time. And this top plot here is a couple of years worth of bicycle rental. So it's a company that rents bikes. They want to know how many bikes to keep out on the street, and they know that the overall trend is going up, and there's the seasonal cycle there, and there's some other stuff going on. So, so that's the response variable, if you will. And as far as predictors go, there's some air temperature. It gets warmer in the summer, which coincides with people rent the bikes. There's wind speed, humidity, all kinds of good stuff to try regressing. Okay. So the thing would be to try to predict, can you predict the total number of rentals based on all these variables? I think the next question is one I stole from Hasty Tishwani Friedman's book. So the thing that Steve was talking about, the cross-validation, is here's a generalized plot that I really like. The x-axis here is model complexity. So here's the simplest possible model. Here's the most complex possible model. The y-axis is the prediction error. And the blue line is the error you get from just looking at the data you're training your model on. So the model sees the blue data, and the model goes, oh yeah, I can make my model as complex as possible. I'll make it really, really complex. Look how low my error is. I'm done. And the thing is, as Steve was kind of mentioning, if the model basically ends up essentially just memorizing that data set, then of course there's no error because you've basically got this incredibly complicated model. The reason you build models in the first place, obviously, is not for that training sample, you're trying to generalize what you're learning about the world. So I mean, the training sample is a doorway into understanding a larger thing, which is, what affects things in the real world. So the test sample is essentially the real world. And the thing about test sample, this is the data that the model has not yet seen. And of course, it's always, the error is going to be greater than the training sample because, of course, in real life, when you look at data you haven't seen before, of course, you'll have a higher error. So that's the first thing. It goes lower. And the thing is, you tend to find a minimum value. If you try to get ahead of yourself over your skis, et cetera, make the model too complex, your error goes up. So if you throw in too many things into your model, in your test set, your training set, it doesn't work for the generalized case. So in terms of some actual coding in R.
Before you move on, Peter, quickly. So you're assuming there, I assume that one of the measures of model complexity is how many variables you have in it, right?
Right. How many variables? So like you have, just one variable here and as many variables as you can think of, throw the kitchen sink in there, you just look up all kinds of stuff. So you have lots of variables. So a few variables on high, right, exactly. Okay, and cool. You can, plus, you can have interaction terms. So you can have, well, it's a combination of the time of year plus the time of day, plus the color of the bicycle. You cannot, it's not just the number of things you consider, but all the interactions as well. So that could also be like the number of trees you have in a forest or something like that. It could make it more exactly, and the number of leaves, all that kind of stuff. So it's stuff like that. Great. So let's actually build a couple of models in R, and the blue is what I'm doing in R. I'm actually building a couple of models here, bikes mod, bikes mod.1. I'm just using a few of these variables. So the temperature is the actual temperature. I'm sorry, the air temperature is the air temperature. The temperature is like the wind chill. It's like how you actually feel, plus the humidity, plus wind speed. Let's just try those. And you can actually ask for the analysis variance. So this ANOVA is the analysis of variance table, which looks at the breakdown, and it gives you this nice, clever, probability value, and it gives you asterisks. Say, hey, actually, all these variables are significant at the 0.05 level, so you get all kinds of nice asterisks. The problem there is, of course, we've all learned to trust those asterisks with our lives, right? Yes, nobody actually knows where the 0.05 comes from. Like as Fisher came up with 0.05, it's like, okay, so where did that come from? It's like, well, nobody knows. He just like, so it's just a number. So 0.05 is just a number, like, well, anyway, interesting point. If you take the model, just reverse these two parameters in the little formula here, you can do the same thing, and you discover, oh my goodness, order actually matters, which is, I actually remember I was completely shocked when I first discovered, like, oh my God, you mean order matters? So you need to have some way of, see what my next slide is. Oh, big complicated thing. So you need to understand what's going on here, and let's get some more information, which is what this next dazzling slide comes in, which is a scatter plot matrix. Basically, I'm not trying to scare everybody, but this is the plot of all the variables against each other. Just a quick note, the way this works is these are all the variables in scope across the diagonal. If I went to take one of these panels here, this little upward bump there, understand what on earth am I looking at? You go to the right until you find a label. That's the label of the y-axis. So the y-axis here is temperature, and go up until you find another label, which is the month. So, hey, we're looking at the temperature as a function of the month, which goes up in the summertime, which is fine. So that's how you read this. It's a kind of a big overview of all the stuff that's going on in your data set. So the bottom row here, the total, remember, is our thing we're trying to predict. So this is a handy little way of saying how does the total on the y-axis depend on all the other variables, each on its own on the x-axis. So you just, say, temperature and air temperature and month, all those things I can kind of see visually correlation there. Mm-hmm. This box right here shows you, hey, no surprise, the air temperature and the perceived temperature are highly correlated, and there's an outlier. And by the way, you don't know which one has the outlier. It's just there's an outlier in there somewhere. You wouldn't know about this just by looking at the bottom row, by the way. So it's important to kind of see what's going on there. So, and if you, speaking of methods to avoid, if you simply say, oh, I'm going to look at each variable independently. Oh, these both have high correlation. Let's just take two variables. Okay, I'll take temperature and air temperature. Boom, I'm done, because they both have a good correlation. Well, you're actually not gaining much by including, once you've got one of these, if you include the other one, you could argue that you're not actually adding very much. You're probably adding some stability because you're getting possibly an independence kind of thing, but there's a danger of just looking at the bottom row and not looking more deeply into correlations and so forth. It's such a useful little tool, right? The scatter plot matrix. It's kind of like the first thing. Yeah. Yeah, I remember I showed this to a client once. They'd never seen it before. They're like, "Whoa!" What? And I had to explain, and they're like, "Wow, this is really useful." So this is kind of a go-to method for, if you have, again, a small number of variables. It doesn't work if you have like 50 variables. It's small, a small amount of data. And there's ways of plotting these as heat maps, little heat map tiles, and distributions and densities. You can get quite elaborate. I would encourage you to look at the G-Galley R package to do some interesting good summaries there. So, and I'm saying, hey, wouldn't it be cool if there's an automatic way to figure out which of the right variables to use? And that's where stepwise comes in. Just to say, stepwise is a way of choosing which variables to include in the model. And in that sense, this is known as a greedy method, which I thought, I was kind of shocked, like who would call a method greedy? Well, greedy means that, to go back to this case, let's say temperature is going to be chosen. So air temperature is never going to be chosen, let's say, in that case. So if I choose some subset, I might choose one and not the other one. And, you'd argue, look, there is actually some information I'm missing out on. So just to be aware that the variable selection makes it easy for your model to be explained to somebody else. Like, hey, my model depends on this, this, and this. I can explain it to some executive, whatever. So in that sense, that makes it easy. But on the other hand, it's a greedy method, and there's disadvantages of that. So two basic approaches is you forward and backward, right? So you start with a very simple model. You add one at a time, and the order is added is that the stepwise says, okay, I'm going to figure out which is the best variable to add. Hey, guess what? It's air temperature. That's the best one. And then given that I've done air temperature, now of the remaining variables, which of those is best? Oh, it's humidity. And you sort of carry on and do this. That's the automatic way. You don't have to think about the best way. Backwards is you do the reverse. You build a model and you pluck off one variable at a time. In this case, they've gotten rid of temperature, which kind of leaves with the other ones there. So we get the same result. And you got these dazzling array of statistics there. You take your pick. And I was telling Stephen, if there was one way to measure this, there would be the one way. But the fact that you see like 15 different methods here to evaluate things means, hey, you can take your pick. So there's obviously a bit of disagreement or some different.
If you don't want to use all the variables, it'll sort of guide you when to stop. Is that the idea?
Right. It kind of guides you. So, sorry?
So how do we decide when to stop?
How do you decide when to stop? So the AIC, I kind of like the AIC, that's the Akaki information criterion. What it does, so residual sum of squares means this is basically always going to go down. That's the blue line you saw in that curve. So the blue line model goes, hey, I'm going to make the model as complex as possible. AIC says, yeah, but you've added a variable here. So it basically penalizes RSS. You decrease the misfits, but you then increase this measure by the number of degrees of freedom in the number of variables, essentially. So if you add, 12 months of the year, each with its own coefficient, you've added 12 variables there, 12 degrees of freedom. And if you've decreased your RSS by some tiny amount, then that's that penalty there. So AIC, you basically look for the minimum AIC before it goes back up again. Like this one, the full model has a higher AIC, so that's kind of how you do that. With a more complicated linear model, have more stuff, you get a deeper thing. And the comment here is that the variables are selected for you automatically, but the order is baked in, right? So if there's a different order, now that you've done all. Sorry?
Can we try all the different sort of orders?
Right. So the next step. So here's the all possible orders, right? So all possible methods, and you get this big complex list. And what you get are these. The all possible tells you, okay, the x-axis here is the number of variables in the model, and the y-axis is, in this case, AIC. You can take, there's actually a number of different diagnostics here. AIC I kind of like. So looking for whichever of these things is the minimum, and each like 2 years. These are all the combinations of 2. These are all the combinations of 3, combinations of 4, and you want to look for the lowest one. And these numbers here, unless you look them up across, you know, hey, 99 is pretty good, or 120 is pretty good. So let's look at it across there. So that's
I see. So let me see if I understand this, Peter. So AIC is like this nice measure because it combines like how well the model fits, but it also, you know, it gets boosted if you have fewer variables. So the less complex but the better fit your model, the better AIC score you get. And what this is showing us is that, well, maybe we can stop with like maybe 5 variables in this combination number 99. Is that how I should read this?
Absolutely. And if you have 2 sort of candidate variables and they both have 1 degree of freedom, and one of them's better at reducing the misfit, the other one is the one that's better to kind of wins. But if you have 2, you know, so-called variables, but one of them secretly has, let's say, code up the day of the week. So the day of the week is encoded in that variable, and since you're actually secretly adding, I guess, 6 degrees of freedom there, but against a linear thing with, and so those 2 variables, let's say, decrease the misfit by the same amount. The one with just 1 variable, if you will be selected because it doesn't get penalized as much. But the one with hey, you just added 6, you know, independent variables there, so it doesn't count. You know, it's basically you're not cheating, but you're adding a lot of complexity there. Yeah, that's the kind of thing there. And I'm going to make a point, but oh well. So again, this is a greedy method.
Can you explain a little bit more what you mean by greedy? I don't think I totally understood that.
Yeah, greedy means, and I did not make up this word, right? So greedy means that so you have a bunch of variables you're trying to model with, and one of them is always in the shadow of the other one. One of them is always a little bit less, has a little bit less predictive power than another variable. So its big older sibling always gets to glory, and the other one is like, hey, you know, I've got some independent information. You know, it may not be much, but it is actually slightly independent of the other one. So greedy means that, yeah, you get a simple model, but at the expense of you're actually not using all the information, which is where the other methods that are more complex, like the stabilization methods, the ridge regression, so forth. The other thing too is that this actually is, so far we're still talking about that blue line, right? In that first plot, you're still talking about the data you're looking at, which is the data you're building a model on. You haven't yet. Yeah. None of these methods look at the out of sample data. So another method to do would be to say, okay, this is actually trying to help you estimate how it's going to work in the real world. Once you let the little thing go flying off on its own, let me see how it does. A more fair method, if you will, would be to use cross-validation to say, okay, look, let's give it some data the model has not seen yet, and let's evaluate the best model in that way. So the complexity can be chosen in that sense as well. So.
But it would still be the same basic idea. You're just running it using cross-validation rather than on the training set.
Right, and the cross-validation has to work with something. So you need a sequence of models in the first place to run your cross-validation on, right? And
so what about,
I guess the point that,
go ahead.
My point there is that actually, okay, so it's all nice, you know, all fun and games here that we can make this nice little plot and find little triangles here. But once you get, you know, I mean, how many data sets have like 5 variables, right? Or 6 or 7, whatever this is. If you have a data set with 50 variables, you know, this gets it's like a combinatorial problem. You get so many combinations of these things that, you know, there's no way you can do this. So this becomes really impractical. So this falls apart. What are some other methods then?
Can you tell us?
Right. So there's ridge regression, and there's lasso, or a couple of different methods, and there's a random forest, which is actually illustrated right here. So here's a random forest method, and the random forest basically works by occasionally leaving, not occasionally, it deliberately leaves out variables. So it'll pick just a subset of the variables to look at and build a model deliberately with a fewer number of variables than the rest and a fewer number of the rows. So it automatically does at a sample a cross-validation. And you get this ranking of the importance, which is measured by, there's a couple of different ways of measuring importance. This is one of them. So the year is important because there's no, I should have included a linear term because it appears to be a linear trend. So the year is the next best thing. And look, here's temperature and air temperature. They're both up there. They're both, you get a pretty good sense of, all right, this is how you get this. And the reason they're both there is that some of the models use temperature and not air temperature. Other models use the reverse. So you get this independent assessment of how important each of these variables are in your model. And then this plot happens to show, is the association positive, negative, or is it whatever? The red thing is random because my colleague David Katz had the nice idea of, hey, just toss in a random number, and this is all a random process. So the random number will have some predictive value, and it'll appear in this little chart there. So
you mentioned Ridge and Lasso as well.
So yes, let's actually go to this one. So so this one here is showing the Team Studio, and of course Team Studio has nice methods like, apart from ordinary least squares, it's got the Ridge and Lasso methods of stabilizing things and choosing parameters. Ridge stabilizes and Lasso basically chooses parameters for you. Ridge is a bit older, Lasso is a bit more modern method. So yeah, so Team Studio is a great way for doing these things, as well as the out of sample stuff. It's probably a good time too.
Yeah, that was great. That was a whistle-stop tour through variable selection. Whirlwind tour, maybe is a better word. And we're actually going to be covering Lasso and Ridge in next month's session, so we can dive into that in a little bit more detail. But at a high level, that's another method, along with correlations that you mentioned, with these measures of variable importance that you get from ensemble. And then, of course, the stepwise methods that you went into there, which I now understand in much greater depth. Peter, thank you so much. That was very helpful. Nina, do we have any questions? Maybe time for one or two before we head out?
Sure. So you didn't mention PCA. Is that a variable selection method too?
PCA is a way of, with PCA, you need all the variables, right? So you basically looking for, it's a dimension reduction method. So so basically in that example, the air temperature and temperature would be lumped into a single element of the PCA, and it would be probably more stable than using each one by itself. So you would sort of combine them. So you would essentially, you can take many variables and reduce them down to, well, you only need these 5 components. But to form the components, you still need all the variables. So if you use PCA, there's a lot of advantages to that, but then you do ultimately need all of the variables used in PCA to apply it in the real world. So, keep that in mind. It's, I like PCA. I love PCA. It's great to understand things, but you deal with these modes, which you have to kind of mentally figure out.
Right. And Peter, there is one more question from one of the attendees. Is it safe to say that variable showing less relevance than a random variable as an input?
That would be correct. Obviously, the ones which are not even as good. I mean, you would do better by using a random variable. That's what it's telling you. So that's what it's telling you. Yeah.
Well, Peter, thank you so much, and we wish you all the best for your retirement. And we will miss all of these pearls of wisdom. And you're welcome back anytime if you get bored.
Of course. Thank you, Stephen.
Yeah. Thank you very much, everyone, and hope to see every one of you in our next session, in June. And stay safe, everyone, and have a great one. Bye, guys.
Thanks a lot. Bye.